We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Getting my feet out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you are listening to episode 100 of the Space Rocket History Podcast. And now, Apollo Preliminary Design. In January 1960, President Eisenhower wrote NASA Administrator Glennan with the following order, quote, "You are hereby directed to accelerate the Super Booster program for which your agency recently was given technical and management responsibility." End quote. This order ensured the transfer of the von Braun group from the Army Ballistic Missile Agency to NASA, and it gave Glennan the launch vehicle development and management capability that he needed. Eisenhower's letter to Glennan was the first indication that the administration might approve something beyond Mercury. At least Glennan interpreted it that way, and told Abe Silverstein, director of NASA's Office of Space Flight Programs, to encourage advanced design teams at each field center and in the aerospace industry. Plans soon came in from both of these sources. Also in January, J.R. Clark of Voight Astronomics sent Abe Silverstein a brochure titled, quote, "Manned Modular Multipurpose Space Vehicle," end quote. It was the work primarily of Thomas E. Dolan. The booklet outlined a unified systematic approach to a national space exploration program leading toward a manned lunar landing mission. In February of 1960, von Braun's team distributed its latest study called, quote, "A Lunar Exploration Program Based Upon Saturn Boosted Systems," end quote. But early in 1960, with Mercury still unproven, chances of winning administration approval to move either of these proposals into a hardware development stage were small. On the other hand, no one was told to stop planning a payload that might fit atop the newly approved Super Booster, and von Braun's team was making good progress on the Saturn I. On March 28th, two of Saturn's first stage engines passed an initial static firing test of approximately 8 seconds duration. It was the first live firing of the Saturn test booster. During a second test on April 6th, 4 engines were successfully static fired for 7 seconds, and on April 29th, all 8 engines of the test booster were successfully fired in an 8-second test. On February 15, 1960, Silverstein told Gilruth to work out a presentation similar to the Vault brochure using the modular concept, which meant designing separate pieces of the spacecraft for specific functions at different phases of a mission. Gilruth gave this task to Robert Pilen's Advanced Design Group. Pilen's team pulled together some guidelines and began presenting them to all the NASA centers. Pilen, Faget, Stanley White, and Robert Chilton spoke, answered questions, and distributed copies of their papers on the aspects of lunar mission planning, leaving the final summary to Gilruth's Associate Director for Development, Charles J. Donlan. Donlan outlined the problems that could be foreseen and solicited suggestions and proposals as to how best this effort could be carried out. Donlan asked specialists at the NASA centers to study such critical areas as flight duration, optimum launch times, propulsion requirements, trajectory analysis, and the effects of the Moon's gravity on lunar orbits. He also cited the need for configuration studies of the lunar landing stage, a 1 or 2 component lunar vehicle. While these briefing sessions were going on, Langley sponsored a conference on space rendezvous in May 1960. Participants from all of NASA's organizations reviewed rendezvous studies underway and discussed likely avenues for further research. Langley was already engaged in studies. John C. Hobart, Assistant Chief of the Dynamic Loads Division, had formed a small group to study soft rendezvous, or how two vehicles can come together at the high velocities required for space travel without crashing into each other. Toward mid-1960, committees and groups within NASA had done as much preliminary internal work as profitable. John Disher and George Lowe persuaded Administrator Glennan that it was time to sponsor a NASA Industry Program Plans Conference in late July to tell of NASA's tentative plans. The administrator approved the awarding of 3 feasibility contracts for advanced manned space flight studies. On July 28th and 29th, 1,300 representatives from government, the aerospace industry, and the institutions attended the first in a series of NASA industry planning sessions. During these 2 days, NASA officials outlined the agency's plan for launch vehicle development and potential projects for manned and unmanned spacecraft. Many of the invitees returned on August 30th to learn about plans for a circumlunar manned spacecraft program and 3 6-month feasibility contracts to be awarded later. Briefings by the Space Task Group's top officials and planners, including Gilruth and Palin, emphasized that Apollo would be Earth orbital and circumlunar and would directly support future moon landings. Any interested company would be invited to a bidders' conference in 2 weeks. Formal proposals would be required 4 weeks later, and the study contracts would be awarded by mid-November. Following the same general format, the bidders' briefing at Langley on September 13th included a formal request for a proposal, a statement of work, and some definite guidelines. Essentially, these ground rules were based upon the assumption that the Saturn booster could launch a lunar reconnaissance spacecraft that would support 3 men for 2 weeks. Palin laid out 4 mission and vehicle guidelines. Manned lunar reconnaissance, number 1. Number 2, Earth orbital missions in conjunction with a space laboratory or space station. Number 3, Saturn booster compatibility, which meant the spacecraft could not weigh more than 6,800 kilograms for lunar missions. And 4, a 14-day flight time. Max Faget stressed return, re-entry, and landing, safe recovery from aborts, ground and water landings with a capability for avoiding local hazards, 72-hour post-landing survival period, landing in pre-planned locations, and auxiliary propulsion for maneuvering in space. Richard S. Johnston presented 3 demands. First, shirt sleeve environment. Second, a 3-man crew. And third, radiation protection. He discussed the need of the crews for a safe environment and for atmospheric control. And finally, Chilton presented guidelines for onboard command, emphasizing man's role as an active participant in the mission and its influence on hardware design, and for communications tracking pertaining to the ground facilities required for flights beyond Earth orbit. Altogether, these guidelines constituted what the Space Task Group would demand of the Apollo spacecraft. The Space Task Group had published the formal request for proposal on September 12, 1960. 88 firms sent representatives to the bidders' briefing, but only 63 actually picked up forms. By October 9th, NASA had received 14 bids. The low number of bids was due to many aerospace firms teaming up, either in partnership or as subcontractors, to vie for the awards. All bidders were told that even the losers should continue their efforts, thus strengthening their chances in competing for the hardware phase of Apollo. NASA assured them that the agency would not limit its choice of the designer and builder of the spacecraft to the 3 selected study contractors. In fact, Space Task Group people met later with representatives from the losing firms and discussed the weaknesses in their proposals and offered to work with them informally to overcome these failings. On October 25th, after the bidders' proposals in trajectory analysis, guidance and control, human factors and radiation, onboard systems, and systems integration had been compared, GOET announced the winners. The team from Convair of San Diego, General Electric of Philadelphia, and the Martin Company of Baltimore. Contracts of $250,000 were awarded to each of these 3 bidders. Convair operated under a more complicated arrangement than the other 2 winners. Using its Fort Worth division for radiation and heat protection, its San Diego plant for life support studies, the Lovelace Foundation and Clinic in Albuquerque for aerospace medicine, and the Avco Corporation's Research and Advanced Development Division in Wilmington, Massachusetts for data on re-entry vehicle design. General Electric's Missile and Space Vehicle Department teamed with Bell Aerospace Systems Company. Martin decided to go the whole route alone. Members of the Space Task Group who monitored the 3 study contracts developed into a 4th group, working out their own advanced designs just as the contractors were doing. This sort of work gave them the confidence they needed to act as monitors for the study contractors and an opportunity to compare their designs with those submitted by industrial experts. Most significantly, perhaps, the systems integration crowd, members who were studying how all the pieces would fit together, soon decided that the Space Task Group's own preliminary design was a good one. The 3 successful bidders began discussions with the Space Task Group on the technical aspects of their task almost immediately, with General Electric visiting its Langley-based monitors first. Donlan appointed 3 liaison engineers to act as single points of contact for the studies. Herbert G. Patterson for General Electric, John Lee for Martin, and William Petnia for Convair. Monthly meetings between these special monitors and the contractors kept Donlan and Pylon informed of progress. Now let's change the subject to the Low Committee. Early in 1960, Administrator Glennan established a Space Exploration Program Council to oversee program planning and implementation. Near the end of the year, Siemens thought it wise to convene that committee, which included Goethe, von Braun, William H. Pickering, Ira H. Abbott, Abe Silverstein, Major General Don Ostrander, and Albert F. Siepert. They met with Siemens on September 30th for a briefing by George Low on Saturn requirements for Project Apollo. Low posed 5 questions and defended his answers to them as proof of the realism of the proposed schedule for Apollo. Question 1. Will the spacecraft be ready in time to meet the Saturn schedule? Number 2. Will the spacecraft weight be within Saturn capabilities? Number 3. Are there any foreseeable technological roadblocks? Number 4. Will solar flare radiation prevent circumlunar flights by men? And number 5. What are the costs of this program? To each of the 5 questions, Lowe made positive assertions of competence and capability. He argued that an Apollo circumlunar prototype spacecraft could be ready in 3 to 4 years, a production vehicle in twice that time. Space Task Group weight estimates showed a reasonable margin between the weight of the spacecraft and the payload the C-2 Saturn could be expected to boost. No insurmountable technological obstacles were anticipated, Lowe said, not even re-entry heating or solar flare radiation. Lowe concluded that the current cost level of $100 million a year would eventually rise to approximately $400 million annually. All of these considerations, in his opinion, argued for an immediate decision to go ahead. But the fact that this planning aimed at lunar circumnavigation rather than lunar landing seemed to be blocking approval of Apollo. NASA's top administrators appeared hesitant to fight for a mere flyby mission to the moon. Lowe recognized this reluctance and on October 17th told Abe Silverstein he was changing the plan to include lunar landing in order to properly justify Apollo and place Apollo schedules and technical plans on a firmer foundation. To this end, Lowe said he and Eldon Hall, Orrin Nix, and John Dishner would try to establish ground rules for manned lunar landing missions, to determine reasonable spacecraft weights, to specify launch vehicle requirements, and to prepare an integrated development plan including the spacecraft, lunar landing and takeoff system, and launch vehicles. The Space Task Group also moved to support a program that would be more than just a circumlunar flight. Gilruth reorganized his people in September, setting up an Apollo Projects office in Max Faget's Flight Systems Division. After getting the feasibility study contracts started, Faget, Pylon, head of the new office, and J. Thomas Markley attended an Apollo-Saturn conference in Huntsville, at which time they reported progress on the contracts. Later that afternoon, Faget and von Braun agreed to work together on a plan to place man on the moon and not just in orbit around it. Gilruth assigned Markley as liaison with Marshall. Spending most of his time in Huntsville, Markley learned the opinions of many of von Braun's group on future vehicles and mission approaches, and became well versed in their preference for rendezvous in Earth orbit rather than direct flight, which would require vehicles much bigger than Saturn as then planned. In December, Markley reported to Donlin that Marshall was studying orbital assembly and refueling techniques and was planning to let contracts to industry for further study on these subjects. During the first week of January 1961, Lowe's committee was formalized as the Manned Lunar Landing Task Group. The expanded team was to prepare a position paper to answer in some depth the question, what is NASA's Manned Lunar Landing Program? How much is it going to cost to land a man on the moon? And how much longer is it going to take? Lowe and his committee met on January 9th. Siemens outlined the group's task in detail. The members were to draft plans for a lunar program describing both direct ascent and rendezvous methods for use in budget presentations to Congress. They were to include cost and schedule estimates for both modes. Developing a plan for manned lunar landing was among NASA's major objectives, the group was reminded, even though the program was not yet approved. During the next 4 weeks, the committee labored over a plan for manned lunar landing and submitted it on February 7th. No major technological breakthroughs, No crash programs and no real physiological barriers were envisioned. The concurrent development of spacecraft and launch vehicles should lead, if financially supported, almost inevitably to a manned lunar landing in 1968 to 1970, they thought. The cost should be peaked around 1966 and total about $7 billion. The big Saturn and the bigger Nova boosters would be built and tested anyway, the group reasoned, and a manned space station in Earth orbit would probably be constructed by them. Low conceived Apollo in 2 phases. First, extended Earth orbital missions. Second, circumlunar leading to lunar landing missions. The Low Committee stated that lunar landings could be made by using either direct descent or Earth orbital rendezvous modes. Launch vehicle development would determine how large a step NASA could take in space at any given time. Moon landings demanded launch vehicles that could lift from 27,200 to 36,300 kilograms into space fast enough to escape the Earth's gravitational pull. But the C-2 Saturn in the agency's fiscal 1962 budget request would only be able to boost 7,000 to 8,000 kilograms to that velocity. It could thus send manned missions to the vicinity of the Moon, but it could not land there and then return its cargo to Earth. The committee cited 2 ways of getting this booster capability for manned landings: either refueling a number of Saturn C-2s in Earth orbit, or building a vehicle large enough to perform the mission directly from the ground. Although both appeared feasible, the Earth orbital rendezvous scheme would probably be quicker. Accordingly, NASA must develop orbital operations techniques. Refueling in orbit would probably be possible by 1967 or 68. And there the matter rested. Early 1961 was an unsettled period for NASA. With the country requiring a new president and the agency a new administrator, the prospect for moon flights was highly uncertain. But Kennedy was deeply interested in space. Before his inauguration, he had appointed an ad hoc committee headed by Jeremy B. Wisner of the Massachusetts Institute of Technology to review the entire missile and space effort. The Wisner Committee's report, quite critical of the way Mercury was being managed and of NASA's apparent bias in favor of manned spaceflight at the expense of the unmanned science programs, called for stronger technical competency within NASA and a redefinition of goals. Because Wisner had joined in the missile gap rhetoric during the November presidential campaign, his committee's report the following January was suspect in some quarters. Nevertheless, it spurred NASA's civil service workers to prove it wrong. The Wisner report also touched off a debate on the choice of a new leader for the space agency. Wisner, like other scientifically oriented advisors within the administration, favored a proven and respected scientist/engineer. Shortly before his inauguration, however, Kennedy had delegated responsibility for space matters to Vice President-elect Lyndon B. Johnson, who was a longtime champion of America's space programs in Congress and architect of the 1958 legislation that created NASA. In contrast to Wisner, Johnson wanted a hard-hitting, politically experienced administrator to preside over the agency. Glennan's resignation from NASA was effective January 20th, but Kennedy did not announce his successor until the end of the month. In the interim, at the request of the White House staff, Dryden was acting administrator. On January 30th, the president ended a spate of speculation by naming James Webb as NASA's new head. Quickly confirmed by the Senate, Webb was sworn in on February 15th. Dryden remained as deputy administrator, personifying scientific interest within the agency. Dramatic changes for NASA seemed likely. Webb was a man with a long and varied background in government, industry, and public service. During the Truman era, he had first been director of the Bureau of the Budget from 1946 to 1949, and later Under Secretary of State from 1949 to 1952. With a forceful demeanor, extravagant style, and a genius for improvisation, Webb soon became a familiar figure on Capitol Hill as a champion of the space program and defender of the agency and its fiscal interest. Webb met with his key officials from headquarters and the field centers at NASA's 5th semi-annual retreat in Luray, Virginia, from March 8 through the 10th, 1961. He announced that Seaman would be the operating vice president of the agency and that the field centers would in future report directly to Seaman's rather than to the major headquarter staff offices as in the past. There were hints of other significant changes that would be needed to manage a program the size of Apollo once it was approved. Webb's ideas were not hatched overnight, but were well-founded, in part at least, on documents passed on to him by Glennan. The principal contribution was a study led by Lawrence A. Kempton, Chancellor of the University of Chicago. Contained in the Kempton report were recommendations that the centers should report directly to the Associate Administrator, that formally established project offices should manage projects, and that NASA should rely more on contracting support. In 1961, many of these suggestions were implemented. Seaman's new assignment was the first step along that path. In late March, President Kennedy began strengthening the space program. He sent Congress a revised fiscal 1962 budget for NASA, raising the agency's funding more than $125 million over Eisenhower's recommended level of $1.1 billion. Much of this increase was earmarked for the Saturn C-2 and the F-1 engine, and was expected to speed up development of these important items significantly. Seaman suggested even greater increases than NASA actually received. Given the funding levels he proposed, manned circumlunar flight with the C-2 would be feasible in 1967 rather than 1969. The F-1 engine, essential to an even larger launch vehicle, was the key to manned landings. Seaman believed the first manned lunar landings depended upon this chemical engine as well as on the orbital and circumlunar programs, and could be achieved in 1970 rather than 1973. More money, he told Webb, will increase the rate of closure on the Soviets' lead in weight-lifting capability and significantly advance our manned exploration of space beyond Project Mercury. Webb forwarded Seaman's memorandum to President Kennedy on March 23, 1961, in response to requests for information about NASA's plans. While NASA's leaders appeared to have pushed Apollo closer to an approved program, activities in the field had also accelerated. The technical liaison groups formed to evaluate the 3 industrial studies had grown to include part-time virtually every senior engineer in the Space Task Group, as well as representatives from other NASA centers. By mid-February, feverish preparations were being made by Donlan's office for separate mid-term reviews of the Martin, General Electric, and Convair contracts. In March, the industrial teams came to Langley one by one and stood before a large audience who had come to hear what the contractors had to tell. Each company followed roughly the same agenda: trajectory analysis, guidance and control, configuration and aerodynamics, heating, structures and materials, human factors, onboard propulsion, mechanical systems, and instrumentation and communications. The NASA auditors commented on the presentations, each of which seemed a bit too general and lacking in the technical information the NASA planners wanted. For instance, Martin Company's team was complimented for its briefing on mechanical systems, but chided for neglecting structures and material analysis related to Apollo design requirements. The General Electric Group scored high on human factors but low in its discussions of mission abort studies, instrumentation, and communications. Max Faget was especially irritated that none of the contractors had proposed modifying and expanding the blunt-body Mercury-style spacecraft. Some experts had predicted that the hot gas radiation heating caused by Apollo's greater re-entry speeds would make this shape unacceptable, but experiments by Ames Research Center indicated that these predictions would not materialize. In addition, Caldwell Johnson, Faget's chief design assistant, had recently finished a study on the advantages of the conical blunt-body command module over the designs of any of the three contractors. William N. Taub of the same office later recalled that the contractors, after the midterm review, had to jump in real fast and come in with a new vehicle based on the Space Task Group's version. Conversely, Mel Barlow of Convair looked at the modified Mercury as only a slight technological advantage. He said he was shocked to learn that NASA intended to keep that configuration. While most of the Space Task Group labored under heavy operational pressures, the 9 Technical Liaisons Group at Langley tried to clarify engineering designs for a spacecraft that would circumnavigate and perhaps land on the Moon. Although they acknowledged that Saturn C2, or its next larger version, should be capable of sending a large payload to the Moon, the questions of how large, by what mode, and with what capabilities were by no means settled or even well defined. In early May of 1961, the first reports from the completed study contracts began arriving at the Space Task Group. All 3 contractors had spent considerably more than the $250,000 NASA paid them. Convair's report depicted a 3-module lunar orbiting spacecraft. Command, mission, and propulsion modules were designed primarily for lunar orbit, with flexibility and growth potential built in for more advanced missions such as lunar landing, with the same basic vehicle design. A total Apollo cost of $1.25 billion over about 6 years was estimated. Convair selected a lifting body concept, much like one conceived several years earlier by Alfred Eggers of Ames for the return vehicle. The command module with an abort tower attached through launch would nestle inside a large mission module. This was similar in its mode of operation to the command and service modules that ultimately evolved for Apollo. Convair envisioned mission planning as building progressively upon many Earth orbital flights before attempting circumlunar and then lunar orbital missions. Earth landings would be by glide sail parachute near San Antonio, Texas. Elementary experiments that would evolve into rendezvous, docking, artificial gravity, maneuverable landing, and an eventual lunar landing were foreseen. The study cost the contractor about $1 million, 4 times what NASA paid the company. The other 2 contractors spent even more of their own money. General Electric's study cost twice as much as Convair's and featured a semi-ballistic blunt-body re-entry vehicle. Had this configuration been selected, the payload sent to the Moon would have resembled the nose cone flown on the early Saturn C1. General Electric's design capitalized upon hardware already almost ready to fly, but it did offer one innovation: a cocoon-like wrapping for secondary pressure protection in case of cabin leaks or meteorite puncture. Although General Electric did not estimate the final cost in its summary, the company was confident of achieving circumlunar flight by the end of 1966 and lunar orbital flight shortly thereafter. The Martin Company produced the most elaborate study of the three. Martin not only followed all the Space Task Group's guidelines, but also went far beyond in systems analysis, focusing on versatility, flexibility, safety margins, and growth. This was the only study that detailed the progression of steps from lunar orbiting to lunar landing. Martin's spacecraft would have been similar to the Apollo spacecraft that ultimately emerged. Later, when the hardware contract proposals were evaluated, Martin scored first on configuration design. Martin recommended a 5-part spacecraft. The command module was a flat-bottomed cone with a rounded apex and a tower for a tractor rocket launch escape system. Behind the flat aft bulkhead were propulsion equipment and mission modules. Trade-offs between weight and propulsion requirements led to the selection of a pressurized shell of aluminum alloy coated with a composite heat shield of superalloy plus charring ablator. 2 crewmen would sit abreast with the third behind in couches that could rotate for re-entry, G-load protection, and for getting in and out of the spacecraft. Flaps for limited maneuverability on re-entry, a parachute landing system, and a jettisonable mission module that could also serve as a solar storm cellar, a laboratory, or even the descent stage for a lunar lander. Almost 300 persons in Martin spent the better part of 6 months and about $3 million on the data and designs for their recommendations. NASA and its Space Task Group might have evaluated the contractor reports at a more measured pace in more normal times, but in April 1961, the month before these reports came in, the pressures to get America moving toward the moon became intense. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.